This video explores the hRISC illusion in MRT-ADF materials, specifically 2PTZBN. We will investigate the role of hot excitant harvesting and the hRISC channel from upper triplet states. MRT-ADF is characterized by atomically separated HOMO-LUMO orbitals, near-unity photoluminescence quantum yield, ultra-narrow emission bands, and external quantum efficiencies exceeding 30%. Most MRT-ADF derivatives have a small S1T1 energy gap, suggesting negligible spin-orbit coupling. The prevailing hypothesis for reverse intersystem crossing, or hRISC, is high-level hRISC, or hRISC, from upper triplet states. Our subject is 2PTZBN with a prompt fluorescence lifetime of around 4 nanoseconds and a delayed fluorescence lifetime of 5 microseconds. The absorption and fluorescence spectra show a tight MRT-ADF emission peak. Computational modeling using HHT-DADFT confirms a favorable energy landscape for hot excitant harvesting. The energy gap between T2 and S1 is 0.31 electron volts, representing a favorable downhill gap. Theoretical calculations support hRISC. While S1 and T1 lack spin-orbit coupling, T2 and S1 show a massive spin-orbit coupling. The calculated hRISC rate from T2 to S1 is high, at 1.23 times 10 to the 9s⁻⁻1. Experimental proof of hRISC is challenging. Higher-lying triplet states decay in picoseconds. Standard time-resolved fluorescence cannot isolate the hRISC signal from direct singlet-state excitation. We implemented a novel two-laser approach. First, a 405 nanometer CW laser populates the T1 state. Second, a femtosecond pulse excites T1 excitons up to Tm. Finally, a streak camera monitors for transient fluorescence from hRISC. Our reality check showed missing fluorescence. Pumping T1 states to Tm failed to produce the expected fluorescence burst. The flatline confirms the expected hRISC pulse is absent with an experimental accuracy. Transient absorption spectroscopy confirms the femtosecond pulse successfully populated the excited states, as evidenced by ground state bleaching and excited state absorption. The conditions for hRISC were perfect. Using the fluorescence ratio, intersystem crossing yield, and relaxation rates, we calculated the mathematical upper limit for hRISC efficiency. The result shows that the maximum possible hRISC efficiency is less than or equal to 3%. The culprit is internal conversion, driven by the energy gap law. The small 0.44 electron volts T2-T1 energy gap drives non-radiative internal conversion at speeds greater than 10 to the power of 11 per second, completely outcompeting the hRISC pathway. Rethinking MRT-ADF design requires structural modifications to suppress internal conversion. We must widen the T1-T2 gap while maintaining a narrow T2-S1 gap for successful hRISC. Key takeaways include the 3% limit on hRISC efficiency in 2PTZBN and the internal conversion bottleneck. A paradigm shift is needed, requiring deliberate structural tuning to unlock hot excitant harvesting.